complex form of Fourier series, where n is varying from minus infinity to plus infinity. Both way it is found. And also we can get our alpha n versus n. It is called double-sided phase spectrum. That is also is coming from complex form of Fourier series. But if we consider the Fourier cosine series, then we'll see that what is the magnitude? It is not fn, it is 2fn. And our n is varying from 0 to infinity. So in a second thing we can get n, it will be 2fn versus n. And this thing is not present, only that thing. So it is called single-sided magnitude spectrum or single-sided amplitude spectrum. So it comes from Fourier cosine series. Okay. And if we plot alpha n versus n, here also only one thing, this side. So it is single-sided phase spectrum. It also comes from Fourier cosine series. So from double-sided we can get the single-sided. How? For fn and 2fn, just a 2 will be multiplied in the magnitude part and the negative part will be removed here. And what's about the alpha n? Only the negative part will be removed. That's all. To get the single-sided phase spectrum. So let's see one problem on this particular aspect. Okay. For double-sided spectrum, our fn versus n will be always even function. And alpha n versus n, it will be always odd. Okay. So next, page number 2, let's see a problem. Sketch the double-sided and single-sided spectrum of xt equal to 2 sine 10 pi t minus pi by 6 plus cos 20 pi t. Note that to plot a double-sided spectrum or single-sided, whatever it may be, you have to express it in terms of exponential form. So sine theta and cos theta will be replaced by their exponential term using Euler's theorem. But for sine, one problem is that one j comes. A sine theta means it is e to the power j theta plus e to the power minus j theta by 2j. So a j comes, that adds to the phase term, that contributes to the phase term. But for cos theta, this problem is not here. For cos theta, it is simply e to the power j theta plus e to the power minus j theta by 2 only, no j. So it's better that we convert all sine terms into cosine first. We convert all sine terms into cosine first to avoid the unnecessary presence of j. So how to do that thing? So xt equal to 2, from sine we get cos. So cos pi by 2 minus theta is sine theta. Okay, cos 20 pi t. So it's everything is in cos. Now we know one more thing, that cos minus theta equal to cos theta. Cos minus theta equal to cos theta. So if we change inside the sign of things, if we change the sign of the inside thing, okay, no problem then. So 10 pi t minus pi by 6 minus pi by t. So 10 pi by pi t minus, it is 2 pi by 3. So we can write it now. E to the power cos 2 cos theta means e to the power j theta plus e to the power minus j theta. For cos, it will be e to the power j theta plus e to the power minus j theta by 2. So half of e to the power j theta plus half of e to the power minus j theta. So it is e to the power minus j 2 pi by 3 into e to the power j 10 pi t plus e to the power j 2 pi by 3 e to the power minus j 10 pi t plus half e to the power j 20 pi t plus half e to the power minus j 20 pi t. There. Now this is our fundamental frequency, the lowest frequency, and that one is the second harmonic. So it is for n equal to 1, it is for n equal to 2. So for n equal to 1, it is about j n omega 0 t. So we can write it f1, okay, f1 bar e to the power j n is 1 into 10 pi t n omega 0 t. This is n equal to minus 1. So f minus 1 bar into e to the power minus j 1 into 10 pi t plus it is a double frequency n equal to second harmonic. So it is f2 bar e to the power j 2 into 20 pi t plus it is f minus 2 bar e to the power minus j 2 into, sorry, it is 10 pi t. So omega 0 is the fundamental frequency here. Omega 0 equal to 10 pi, fundamental frequency. So what is f1 bar? F1 bar is e to the power minus j 2 pi by 3 or 1 angle minus 2 pi by 3. F minus 1 bar is e to the power j 2 pi by 3 or 1 angle 2 pi by 3. Okay. F2 bar is half, just this, or half angle 0. And F minus 2 bar is also half. So it is half angle 0. Therefore, we can say our F1 equal to the magnitude 1, okay, and alpha 1 equal to minus 2 pi by 3, its angle. F minus 1 is 1 here, and alpha minus 1 is plus 2 pi by 3. Similarly, F2, the magnitude is half, and alpha 2 is 0. And F minus 2 magnitude is half, and alpha minus 2 0. So from this expression, we can get it easily. So once we know, now we can easily plot, okay, the double-sided and single-sided spectra. Complete. So next page, page number 3. So if we plot Fn versus n, now our F1 is 1. Okay. So our F1 is 1 and F2 is half. For n equal to 1, this is 1. Okay. For n equal to 2, this is half. Okay. The F minus 1 is also 1, and F minus 2, this is half. This expression. So F1 is 1, F minus 1, 1. F2 half, F minus 2 half. Okay, n. And n omega 0 is what? It is omega 0 to omega 0. Omega 0 means what? Our omega 0 is 10 pi already. Okay, 10 pi. So it is 10 pi. It is 20 pi to omega 0. This is minus omega 0 or minus 10 pi, minus 2 omega 0 or minus 20 pi. In terms of hertz also we can plot it if we want. Now if we divide it by 2 pi, it will be 5 hertz. Okay, F0 equal to omega 0 by 2 pi. So it is 10 pi by 2 pi. So 5 hertz. So 5 hertz, 10 hertz. Minus 5 hertz, minus 10 hertz. In all such cases, we can get it easily. Okay, so that is a double-sided magnitude spectrum or double-sided amplitude spectrum. And it is obviously our one even function. Last day I told you. What's about our alpha n? N equal to plus 1, n equal to plus 1, plus 2 pi by 3, right? 20 pi. It is minus omega 0, minus 2 omega 0, minus 10 pi, minus 20 pi. In hertz also we can plot it. Minus 10 hertz, minus 5 hertz. It is 5 hertz, 10 hertz. So it is always an odd function. Last day I told you the reason. So it is double-sided phase spectrum. Double-sided phase spectrum. Yes. Now in Fourier cosine series, we find that our magnitude of cosine term is 2fn, not fn, 2fn. So it will be, it has to be doubled, and negative part will be removed for single-sided spectrum. So 2fn versus n. So just take double. Instead of 1, it will be 2. And instead of half, it will be 1. Okay, it's single-sided. Negative part is not there. Okay. Similarly, you can put it omega 0 scale as that one. So it is single-sided magnitude spectrum or single-sided amplitude spectrum. Okay, it's coming from Fourier cosine series. And for alpha n versus n, the negative part will be removed only. That's all. Sorry. This one. Minus 2 pi by 3 is 0. So negative part is removed. So single-sided phase spectrum. So that's how the concept of double-sided and single-sided spectra, okay, is coming. Now, we are almost at the end of the discussion of Fourier series. Okay, one more thing that is required also for our later purpose is that some properties of Fourier series. Some properties of Fourier series. Let's see. So I go to the next page. So it's page number 4. Some properties of Fourier series. The first property is the linearity property. If Fourier series of xt gives rise to a Fourier coefficient Cn, Cn means it is the general form of An, Bn, Fn, any Fourier coefficient, okay, where Cn is the Fourier series coefficient of xt, then Fourier series of yt is dn. Sorry, and Fourier series coefficient of yt is some signal yt is dn. Then, so we have two signals, one xt, another yt. For xt, we are assuming that Cn is the Fourier coefficient of this thing, An, Bn, Fn, anything of xt, and dn is also the Fourier coefficient also. So I am not writing here this one. Okay. Then the Fourier series coefficient of, okay, capital A into xt plus capital B into yt, where A and B are the two constants. Its Fourier coefficient will be capital A into Cn plus capital B into Dn, where A and B are the weighting factors with which the two signals are combined. The two signals are linearly combined. Next, our time shift property. Okay. If Fourier series of xt is Cn, then Fourier series of xt minus t0. The signal is delayed by some time t0. It is e to the power minus j n omega 0 t0 into Cn. Okay. So it means that what is the magnitude part here? What is that representation in polar form? It is one angle. It's it's one angle e to the power minus j theta. So it's minus n. I write it here. So it's one angle minus n omega 0 t0. Okay. And for Cn, its coefficient may be some, its value may be say some Fn angle alpha n. Then when they are multiplied, then result is some Fn angle alpha n minus n omega 0 t0. We know after multiplication in polar form, magnitudes are multiplied, but phase angles are added. So therefore we can say that after time shift of a signal, its magnitude or amplitude spectrum does not undergo any change. The change does not undergo any change. The change is reflected in phase spectrum only. So if we plot phase spectrum versus n, there is a phase spectrum versus n, there is a change. But in magnitude spectrum, it does not have any change. Okay. So that's why from phase property only, we can have the idea whether a signal is shifted in time or not. Next. Time reversal. Okay.
খাতাটা একটু নিচে করবেন।
Time reversal. If Fourier series of xt gives rise to a coefficient Cn, then Fourier series of x minus t, okay, so the signal is reversed in time, will give rise to the coefficient where n will be replaced by minus n. So when it is flipped in time, it will be flipped in frequency also. So all the negative frequency components will become positive frequency component, and positive frequency component will become the negative frequency component. Okay. There are interesting observation here. You know that in our case always the time is moving in the forward direction. Forward direction means it is actually called the thermodynamic arrow of time. Those who have read the book A Brief History of Time by Stephen Hawking we'll know the concept, the thermodynamic arrow of time. In thermodynamic arrow of time, our time moves in such a direction where the entropy of the universe increases. We can break a cup and dish. Okay, it is easy to break, but if we want to construct it, we have to put more energy to bring it into the order. Get my point? So the thing is that always things, once it is broken, cannot be constructed without application of energy. But once we apply energy, okay, it means that more heat is generated in the universe. So the molecules and the particles are undergoing more random motion. So the randomness of the universe increases, or the erratic behavior or the entropy of the system increases. So our time moves in such a direction so as to have more entropy in the system. Okay, that is possible in our case. So that is a thermodynamic, okay, arrow of time. That can be correlated with the expanding universe also. Our universe is expanding actually. But if we think of a case where our universe is shrinking, not expanding, our thermodynamic arrow of time may be reversed. In that case, we may proceed in the reverse direction of time. Okay, at least theoretically. Okay, there are many other things also related to that. Just so in that case, our t will move in the negative direction. In that case, the Fourier coefficients, okay, will not be found as c, it will be found as c minus n. Okay, so that is the concept of time reversal. Next, so many other interesting things can be said on this particular area. I just want to give you the reference of one student, your senior, Pinag Banerjee, okay, in the final year of our department. When I started taking the measurement class in the second year, Pinag Banerjee, after 1 or 2 classes, Pinag came to me just outside of the class. He told me, sir, I don't want to study electrical engineering. Actually, my parents forced me, and that's why I came here. Actually, I love physics, so I want to study. Is it possible to shift to physics from electrical engineering? I told him, to my knowledge that time, how he can proceed. But I advised him, you first complete the electrical engineering seriously. At the same time, you can study on your own on the physics. Okay, ultimately he continued that way. This year, in the JAM exam, like GATE, GATE is for pursuing hard study in engineering, and JAM is for pursuing hard study in physics in the IITs. Okay, he got a fantastic rank. Really, I cannot remember it. Pinag Banerjee. He got a fantastic rank, and he is now going to change his career from electrical engineering to physics, that he loves most. So ultimately the thing is, engineering and physics are related very much. So if you want to shift to the physics also, that is possible for you in the future. So our signal processing, this subject gives, if you study thoroughly and deeply, it will give you an exciting world of physics actually. Okay, through this subject you can realize, not only this, there are many other subjects from which you can have the essence of physics. Okay, now I want to shift to the next property, time scaling. Now, if Fourier series of xt is Cn, then Fourier series of x at, A is a time scaling factor, that is also Cn. Now, if A is greater than 1, signal is compressed in time. If A is less than 1, signal is dilated in time. But whether a signal is compressed or dilated, okay, its Fourier coefficient Cm will remain same. But one change will definitely happen. What? The fundamental frequency is multiplied by A. Just I can give you one example, it will be clear. Consider we have a signal, okay, it's just xt and x3t with one example. Now consider one signal xt and another signal x3t. Say for n equal to 1, it's for xt, its fundamental frequency is say 40 Hertz. Just as an example. For n equal to 3t, what will be its fundamental frequency? The signal is compressed 3 times. The signal is compressed by a factor 3. So its time period will be shorter by the factor 3. Therefore, its frequency will be increased by the factor 3. As it is squeezed by a factor 3, its time period is reduced by factor 3. So frequency is increased by factor 3. So fundamental frequency will be 120 Hertz. Fundamental. For second harmonic, what will happen? This 40 into 2, 80 Hertz. Here it is 120 into 2, 240 Hertz. But what is the ratio of their harmonics? This by that is equal to 2. Here also this by that equal to 2. For n equal to 3, what happens? 40 into 3, 120 Hertz. 120 into 3, 360 Hertz. See, in all such cases, this by that is same as this by that. This by that is same as this by that. So the n does not change. Okay. But the omega 0 and all other values of frequency will change. So all of the values will be changed by the factor A, but the ratio of the two successive frequency will remain same. Therefore, our n will remain same. So our Cn will remain same. Yeah. Next property, multiplication. If Fourier series of xt is Cn and Fourier series of yt is dn, then Fourier series of xt into yt is summation Cn dn minus L, where L is varying from minus infinity to plus infinity. It can be proved. I am not going to that particular thing. Everything can be proved. So when it is multiplied in time domain, in frequency domain, it is something like a, not exactly a convolution, because in convolution it will be L minus L. But some change is there. So I'm not, you know, 6. Next is the conjugation property. If Fourier series of xt is Cn, then Fourier series of xt star complex conjugate so Fourier, its complex conjugate will be C minus n star. Here we have assumed that xt is a complex signal. Here xt is a complex signal. It means what? xt consists of two different signals that are orthogonal in nature, means the effect of one signal does not come on the other, but they have a composite effect. I already explained what we mean by complex signal long back. So xt is a complex signal. So our Fourier series of its complex conjugate is a Fourier coefficient where n will be replaced by minus n, and then we will take the complex conjugate of that thing. Clear? So that is our conjugation property. Now our last property. So I go to the next page. Page number 6. Parseval's theorem. Parseval's theorem. What is that? The power of a signal, power of a periodic signal can be stated as 1 by T0 integration T0 to T0 plus capital T0 xt into xt star dt, or 1 by T0 mod xt square dt. That is a time domain evaluation. Okay. That now it can be proved also that it is can be written as in frequency domain as summation fn bar into fn bar star, n is varying from minus infinity to plus infinity, or it will be f n star, n varying from minus infinity to plus infinity, where fn is nothing but mod of fn bar. So in using frequency domain coefficient, we can evaluate it. Or now fn is what? We know it is equal to a0 when n equal to 0. Now our fn bar equal to f0 or a0 when n equal to 0, and is half of n minus jbn when n is not equal to 0. Therefore, it can be proved that summation fn square can be written as a0 square plus summation n square by 2 plus bn square by 2. Therefore, the power of a signal can be written as summation fn square this way, or a0 square plus summation n square by 2 plus bn square by 2. That way. Two expressions. This is called Parseval's theorem. In frequency domain, using the coefficient variable n, we can evaluate the power of a periodic signal whose Fourier coefficients are known. There, whose Fourier coefficient is known. Now, how to prove that thing? It's very easy. Just I'm giving you just the proof for this particular thing. Now, P equal to 1 by T0, its power, its expression is something like, okay, xt into xt star dt. Okay. It is xt into, now what is xt? We can express it in terms of fn bar. in terms of complex exponential form of Fourier series, we can write it this way. So it is and its complex conjugate. It particular term is this one. So it is a complex exponential form of Fourier series. I already explained it in our last class. This one xt equal to this one. So xt star will be the whole thing star, complex conjugate of the whole thing. Clear? Now once we take the complex conjugate of that thing, it will be fn bar star will come and its complex conjugate will be what? E to the power j theta. After complex conjugate will be e to the power minus j theta, because here it is cos theta plus j sin theta, and when your star comes it will be e to the power minus j theta, means cos theta minus j sin theta, complex conjugate. So sign will change in the angle. So ultimately it will be what? Page number 7. Since it's one important property, that's why I have given a proof of that. For all other properties, you can have a proof. So it will be n varying from minus infinity to plus infinity, fn bar star e to the power minus jn omega 0 t dt. Now we can rearrange the whole thing. So 1 by t0. Okay. Summation, we are taking the summation sign outside. Okay. Then fn bar star we are writing. Fn bar is not a function of t, so it can be taken outside. So it will be xt, then e to the power minus jn omega 0 t dt. Clear? That one. But this is what? This is actually, you know, our, I can show you the expression. Just wait 1 minute. This one. Our fn bar is 1 by t0 integration that x to the power minus j omega 0 dt. The last class we got the proof. So this is equal to, fn bar. So for that integration it will be t0 into fn bar. T0 into fn bar. So it is 1 by t0 summation. It is t0 into fn bar. That expression. T0 cancels. So summation fn bar and fn bar star. So it is proved. From that we can get it fn square. Okay. So that is the Parseval's theorem. Now let's see one problem. That's all about the properties of Fourier series. Let's have one problem. Find the, okay, but before that I want to make a comment that it is the Parseval's theorem using Fn. We are getting this, and we can also use that expression. Note one thing, that when we use one set of coefficient like Fn, then our n is varying from minus infinity to plus infinity, double the range. And when we have two sets of coefficients, n and bn, then only half the range is used. It is a single-sided expression. So n is varying from 0 to infinity only. When two coefficients, two sets of coefficients, half the range. When one set of coefficient, double the range. So it's a double-sided expression, not single-sided. It is an expression using double-sided spectrum. It is an expression using single-sided spectrum. And we also know one more thing, that n is what? It is the amplitude of cosine term. Amplitude of cosine term, and bn is the amplitude of sine term. So what is the RMS value of cosine term? An by root 2, and square of the RMS is an by root 2 whole square, which is the power. Similarly for sine term, its amplitude being bn, its RMS value is bn by root 2, and power is square of the RMS value. So Bn by root 2 whole square or Bn square by 2. And so these are the RMS power. So it's the power associated with the AC component. Okay. So power associated with the AC component of xt. And A0 is what? It is the power. It is the power associated with the DC component of xt. To the DC component. So total power is the power contributed by all the components. This AC component of power, DC component of power, using this concept, you will do much more thing using in a subject called power electronics. In a subject power electronics. Long back in our department, I used to teach power electronics also, but nowadays, because of too much of loading, I have to shade the load. So I don't do it. Some other obviously teachers will teach you. There you will just see all these type of things. DC power, AC power, all these things of a particular waveform of a particular signal. Clear? So let's go to a problem. Now find the average power of the signal xt equal to 2 sine square 2500 pi t cos 20,000 pi t. If this signal is transmitted through a filter that blocks DC and frequencies above 12 kilohertz, compute the ratio of received power to transmitted power. Let's see what they want to mean actually. Say there is a filter. What is a filter? Any LTI system is a filter. So any LTI system is a filter. Why? Because this system allows certain frequency to appear at its output and blocks the other frequency, okay, from coming to the output. So if we apply input, then some of the frequency component of the input will be available at the output, and some other frequency components of the input will not be available at the output. So it's the system characteristic depends on the frequency. System characteristic depends on frequency. In other words, It is filtering frequencies. Any LTI system is filtering frequencies. Therefore, it is behaving as a filter. Therefore, it is behaving as a filter. So that is the conceptual understanding. How LTI system behaves as a filter. Means a frequency selective system actually. So if we apply XT, we get some output YT. Now PT is the power associated with XT. This power is transmitted. PT is what? Power associated with the input XT, which is okay. Transmitted or applied to the filter. And what is PR? PR is the power associated with the output YT, which is received at the output end of the filter, which is received at the output end of the filter. Yes. Now first compute, first just consider the case of XT, its expression. 2 sine square something into cos something. I write it in the next page. Okay. I write it in the next page. Page number 8. Now, xt equal to 2 sine square two sine square theta is 1 minus cos 5000 pi t into cos this. So the simplification. Now it's not yet complete. Cos A cos B is half cos A plus B 25,000 pi t minus cos A minus B or B minus A. So 15,000 pi t. So what is the power PT? Average power. Average power of XT. So if you integrate it, take the average, you'll get the same thing. Or according to Parseval's theorem, also you can get it directly. According to Parseval's theorem, it will be what? It will be summation of n square by 2. So its amplitude is 1. So 1 square by 2. Its amplitude is half. So half square by 2. Actually, this by root 2 squared. This by root 2 squared and that by root 2 squared. So ultimately it is 3/4 unit of power.
স্যার ওখানেও হাফ হাফ আসবে না 15,000
হ্যাঁ বলো কি বলছো, শুনতে পাচ্ছি না।
15,000 এও হাফ আসবে না cos 18,000 এর আগে
হাফ এখানে না, এখানে তো হাফ আসবে না। cos a cos b মানে কি হাফ? ও হ্যাঁ, এখানে হাফ আসবে। থ্যাংক ইউ, রাইট। So that is PT. Now it is clearly mentioned in the problem that the filter blocks DC and frequencies above 12 kilohertz. In the signal, there is no DC component, so nothing to block. But there are frequencies above 12 kilohertz. That will be blocked by the filter, and this component will not come in the output. So what is that? So what is that block? It is. So what is its frequency? It is this by 2 pi is 10 hertz or kilohertz is kilohertz frequency. This is what 12,000 pi by 2 pi. So it is 12.5 kilohertz. And this frequency is 15,000 pi by 2 pi, 7.5 kilohertz. So this frequency is above kilohertz, 12 kilohertz. So it will be blocked by the filter. Okay. So that will be blocked by the filter. It will not come at the output. The received signal is cos 20,000 pi t minus half of 12 component is blocked by the filter. So what is the received power? Is so 1 square by 2 plus half square by 2. So after simplification, it is 5 by 8 unit. So what is the ratio of received power? It's asked in the problem. Compute the ratio of received power to transmitted power. So ratio of received power to transmitted power equal to PR by PT, which is 5 by 8 divided by 3 by 4, which is 5 by 6. So not all the powers are available at the output. Actually, some of the frequency component is blocked by the filter always. And those frequency components carry some power. So this power is also not available at the output. So always the output power is less than the input power. Always the output power is less than the input power. But in the field of electronics, sometimes a term is used which is called power gain, where output power is more than input power. Can you tell me how this is possible? Power cannot be gained, we know, according to the energy conservation principle. But how it's possible, a power gain? Any idea? In electronic circuit, we
So
compute that,
from
yes. Huh?
sir,
Yes.
from noise of DC source.
No noise. Noise is really a very small amplitude, it's not contributing. And the noise is omnipresent. It is present. If it is present in the input, it is present in the output also. The pattern may change. The thing is that, actual reason is that, for all the electronic devices, the biasing supply is there. Plus VCC, minus VCC. In the op amp, you know, in the transistors, you know, biasing supply is required. Those biasing supply is delivering some bias current to the device. So when we consider the input power to the device, the biasing supply is not considered. Its power, its value of voltage, current, these are not considered in the computation of power of input and output directly. So what happens when we compute the power associated with input, we get some value. Now when we compute the power in the output side, then the biasing supply will deliver some extra amount of power. That power becomes available at the output side of the device. Okay. Therefore, the power of the output signal is more than the power of input because of the power contributed by the biasing signal. So in the input side, this power is not there, but in the output side is there. That's why if we don't consider this biasing supply in the input side, therefore this extra contribution is enhancing the power at the output. So obviously now you understand that the energy conservation principle is not violated here. It is maintained here if we consider the biasing supply. So that is the reason. Okay, next. So that's all about this. We are almost done with the Fourier series. Only a small thing is there as a comment, that we know any periodic signal can be expressed in decomposed in terms of Fourier series. But does it mean that for all periodic signal it is possible? No. The signal must satisfy a set of conditions. Okay, what is that? Let's go to our concluding, okay, comment, that what is the condition of existence of Fourier series of a signal? Dirichlet condition. Dirichlet condition. The condition of the existence of Fourier series of a signal. Condition number 1 is xt must be absolutely integrable over any period, say t0. That is, absolutely integrable means we'll take the absolute value of xt and then its integration will have a finite value. So it will be mod of integration mod of xt dt t0 to t0 plus capital T0. It should be less than infinity. So it should be absolutely integrable. If that condition is not satisfied, its Fourier series, the signal does, although it is a periodic signal, it cannot be expressed in terms of Fourier series. That is condition number 1. Example, consider a signal so this wave it's going on 3 pi by 2 minus 3 pi by 2. So it's a periodic signal. Clear? But note that if we take mod of xt, what it will be? If we plot mod of xt, it will be going this way. Something like in one cycle. In the next cycle also, it will be going there. This way. So if you take mod of xt, if you take mod of xt, then its area will be what? So this is our integration. It's the integration, since it is going towards infinity, its area will be infinitely large. So that will be infinitely large. So the Fourier series of xt is not possible, does not exist. Therefore, our xt is not absolutely integrable. It's not giving us any finite value. Not absolutely integrable. Hence, it cannot be expressed in terms of Fourier series. You know, this is a type of function called tan function, tan t. A tangent function, tan t, cannot be expressed in terms of Fourier series because tan is, you know, sine by cos. So you cannot express it as an infinite sum of sine and cosine, although it is a periodic signal. It violates condition number 1. Now condition number 2. xt must have finite number of maxima and minima over any complete cycle. xt must have finite number of maxima and minima over any complete cycle. So within one cycle, how many maximum and minimum values are possible? That may be 10, that may be 10,000, but infinite number of peaks, crests and troughs, and that is in finite cycle or one complete cycle, that is not practically realizable. In mathematics, this type of functions do exist, but in engineering we don't get. Okay, so it must not have a, so ultimately in our engineering context, this type of signal is not existent practically, so it's not very important in your context. The condition number 2 is not important, very much important in our context. Automatically our xt has finite number of maxima and minima over any complete cycle in the context of engineering. And number 3, last point, xt has, so it must have, right, finite number of xt must have no, xt must have finite number of discontinuities over any complete cycle. It is also automatically satisfied in engineering context. In one cycle, infinite number of discontinuity is not really possible for us. So therefore, it's Fourier series. When it is there, then Fourier series is not possible. Okay, so that is the condition. Now, a final note that if there is any discontinuity at t equal to alpha for the signal xt, and now we express its Fourier series, the Fourier series does not show any discontinuity of the original signal. Rather, it will return a value which is average of the two neighborhood value. So I should write that if there is a discontinuity of xt at t equal to alpha, its Fourier series expression returns a value which is the average of its neighborhood value at t equal to alpha. That is x alpha equal to x alpha plus x alpha minus and half of that. So the average of the two neighborhood value will be returned by the Fourier series at the point of discontinuity, although originally the signal does not have any value at that point of discontinuity. So that is the drawback or shortcoming of Fourier series. Otherwise, it is fantastic. And from the Fourier series, actually, lot more concepts of signal processing emerges. So one more concept we'll see in our next class, from our next class onwards. ঠিক আছে? Anything? তাহলে আজকে এই অবধি ফুরিয়ার সিরিজ থেকে এরপরে একটা দারুণ সুন্দর একটা ইন্টারেস্টিং কনসেপ্ট আমরা পরের দিন শুরু করব, যেটা নিয়ে অনেকগুলো ক্লাস আমাদের চলতেই থাকবে। ঠিক আছে? ওকে।